This is a video that I meant to include with the post for last Friday, but forgot. So here it is, and this will make question number 1 on Friday's homework a little easier. Sorry about that, guys. First, the force on a current carrying wire. Force on a current carrying wire is given by the cross product IL cross B. Now this should look somewhat familiar. It's derived from F equals QV cross B. And it's just the recognition that for a current carrying wire, remember that current is charge over time, whereas in this equation QV would be charge times distance over time. And so we just move the distance out, and the time over here, Q over S, is our current. So force is current times length of the wire carrying the current crossed with the magnetic field, very similar to QV cross B. If you're asked to figure out the strength of the magnetic force on a current carrying wire, the cross product reduces to, mathematically, F equals I times L times B times the sine of the angle between them. And often, especially on the AP exam, the most you'd be asked to do is just two parallel wires or a single wire in a magnetic field where the wire is perfectly perpendicular to the field, and so there usually wouldn't be any theta for you to deal with. And in that case, the equation reduces to, and this is hard to type on a iPad, so I'm going to do kind of some curly stuff. You may see this written on the AP formula sheet in a different order and with some curly letters, B, I, and a curly L. B is the magnetic field that the wire is in, I is the current in the wire, and L is the length of the wire that's contained in the magnetic field. Now usually you won't be given one super tricky, but if part of the wire is not in the magnetic field, you have to subtract that when finding L, so L is the part of the wire in the magnetic field. And now a quick example. How much current is flowing in a 4.8 meter long wire if the maximum force on it is 0.75 newtons when placed in a uniform 0.08 Tesla field. And it's saying maximum force to let us know that there's no angle between the wire and the magnetic field. If there were an angle, that force would decrease because sine of 0 is 1, and then as you increase sine up to 90, it gets smaller and smaller and smaller until at 90 it hits 0. So let's use the formula we just learned. The force vector is the current vector times the length of the wire crossed with the magnetic field vector. And if we're just worried about the numbers and not necessarily the direction, this reduces to F equals I L B, or BIL. Multiplication's commutative, so it doesn't matter what order you list them in. And since we're looking at the maximum force, we know they're perfectly perpendicular, so sine would be 90, or the angle would be 90, and sine of 90 turns into 1. So now I'm just looking for the current, so let's solve this equation for current. I'll divide by LB on both sides, and the equation turns into F over LB equals I. And so that would be, now substituting in, 0.750 newtons over 4.80 meters. And if it weren't in meters, you'd have to change it because meters are our standard international unit. 0.0800 Teslas. And if you grab a calculator and do out that math. Okay, so in doing all of that, I found that there are about 1.95 amperes of current going through that wire. Pretty simple equation. I was reminded that you'll need it because we're going to be doing more with this equation this week, so it's kind of unbelievable that I forgot to put this up with the last video.